Hello everyone and welcome to Altium Academy. I'm your host, Zach Peterson, and today we're going to be going over a very timely topic, and that topic is the use of ChatGPT and related generative AI tools in PCB design. So if you haven't been living under a rock for the last 6 months, you're probably aware that there is this thing called ChatGPT, and you're probably aware that it can generate responses to very complex questions, including technical questions of the sort that you might ask if you're a PCB designer. In this video, we're going to critique some of those responses from ChatGPT. We're going to see how accurate it really is, and we're going to see if it overgeneralizes things and whether or not you can get it to really drill down to the answers that you want. So I think this is going to be really fun, and we're going to do it all live. So let's go ahead and get started. So before we get into some demo prompts with ChatGPT, I think it's important to realize what this thing is actually doing and what it is capable of doing. ChatGPT cannot read your mind. That should be obvious, but I say that because when you actually ask ChatGPT a question, you have to be specific. If you ask a generalized question, you're going to get a generalized answer. So that's the first thing you have to note. It actually follows your lead in terms of generality or specificity. The second thing to note is that ChatGPT is not going to lay out your board for you, and it doesn't replace the skill of somebody who knows how to use design applications or software. That's really important. It can't reproduce or replace the skill of a human. So just because you have access to something like ChatGPT, there's no replacement for time and experience spent using PCB design software. Last but not least, just because you give it a bunch of components or a bill of materials, it doesn't necessarily have the ability to reproduce a circuit or create a circuit that is going to do exactly what you need it to do. I think this is also really important, although there are some tools on the horizon that are focusing on exactly that type of generative design. But because ChatGPT is operating off of text prompts, it doesn't necessarily have the ability to create that kind of documentation or CAD data for your design. And this goes back to my first point. It can't read your mind, so it doesn't know your engineering intent. Just because you give it a bill of materials and you tell it you need a design that does A, B, and C, it doesn't necessarily have the ability to hit all of those different constraints that you give it. So with all of this in mind, let's take a look at some ways that you can use ChatGPT. So I have my instance of ChatGPT up right here. I have, as you can see here on the side of the screen here, several questions that I have been asking the system over the past weeks and months. So just as an example, you can see here I have component specs, I have something about prepreg thickness, I have some stuff for taxes because it is tax season here in the US, and then industry standards, stuff like that. So just as an example, let's take a look at something interesting it can do, such as some simple calculations. Can it do math, and can it do engineering math? Well, I've pulled up one of my old conversations here that was done with the default 3.5 model, so the GPT 3.5 model. This is a pretty simple question that you might ask ChatGPT. So, for example, what is the voltage output from a full wave rectifier? This one should be well known. It's essentially just the absolute value reaching the peak voltage of that AC signal. Now you can see here that it also correctly adds in the diode voltage here for the bridge rectifier. So in a full wave rectifier circuit, in the ideal case, you would essentially have the output being approximately equal to the input minus whatever the drop is across the rectifier diodes. So the rectifier diodes depends what the material in that diode is, but could be about a half a volt, and then it does correctly give that output voltage. A follow-up question, what is the peak voltage? So VP. So what would the peak voltage be, for example, a 115 volt AC signal? Here you can see that it does correctly calculate the peak voltage for the AC signal. So we have the RMS value, which is our 115, multiplied by square root 2 to get to the peak voltage, and then you can see here it calculates it, gives you the value to 2 decimal places, and you can see here I went through several different iterations of this just to then see what else it generates. You can see here that I've got some different variations that I've generated for this part of the question. It will take the peak value as 115 volts and calculate the RMS from it. It will take the RMS value and then calculate a peak value from it. So for this variation, this is actually incorrect given the context of this 115 volts AC signal. So generally when we say 115 volts AC, it is assumed or should be known that the 115 volts here is the RMS voltage and not the peak voltage. So in this particular generation, it actually used it as the peak voltage and not the RMS voltage. So it did this portion incorrectly given the context of the question. However, for some other variations on this, you can see here that it does do it correctly in this generation, and it does it correctly in this generation. So for this question, it gets 4 out of 5 correct. I'd give it an 80%, so I'm giving it a grade of B. This is a pretty simple question. It's not that it did the math wrong here, it's just that it has the context incorrect. So maybe I'm being a little bit harsh of a grader here, but it does do the math correctly. So what about something more complex? What about something like an industry standard? Now, industry standards are one area where I've made a lot of use of ChatGPT, and one of the reasons is that some industry standards have a lot of technical information in them, and unfortunately, I just don't have time to go through and spend hours researching every single industry standard. However, if you take a look over here at, for example, PCB cleanliness standards, here I have generated some information on PCB cleanliness standards by asking several different questions. Now, PCB cleaning standards are specified in IPC, and if you don't know what the standards are, ChatGPT will of course tell you. It immediately picks out IPC 610, IPCJ STD-001. So 2 common cleaning standards. Of course, you can then drill down a bit further. What are some of the various reasons for cleaning printed circuit boards? Some of these are just a little overgeneralized. So for example, improved aesthetic appearance. Some of these are a bit more specific, like removal of flux residues. So removal of flux residues would be one more area that you could then start researching deeper, either with ChatGPT or on Google. Same thing with contaminants. At least here with contaminants, it does get a little more specific, specifically citing dust, dirt, oils, and fingerprints, all things that can contaminate the surface of a PCB and might need to be cleaned. So for these 2 questions, definitely give it high marks because it did mention some of the correct points. The only thing I think that is an issue here, which I mentioned earlier, is that sometimes the answer is a little overgeneralized, and then you need to drill down a bit further. So just for example, with removal of contaminants. Well, if you drill down a bit further about contaminants, you can then follow up with this type of question. What type of contaminants? Here is where it starts to get a little bit repetitive, and then it starts to just repeat some of the things that it mentioned in the previous question. To its credit, it does bring up metal particles. So metal particles like solder balls, metal shavings, all of these different things could sit somewhere on the surface of a PCB, and a cleaning process can remove that. Environmental contaminants were also not mentioned in the previous question. We get them down here. So I think this is important because it illustrates that sometimes you need to drill down just a little bit to get a little bit more information as far as at a high level what you might be dealing with in this type of technical question. So I think what we just saw in the previous example is really interesting because what it shows is a strategy for using something like ChatGPT. Start at a high level with a general question, and as you get to learn more and more about that answer and more about that topic, then it helps you drill down to more specific questions that you can ask to then get to finer and finer detail and increase your knowledge that way. So I think this is exactly how a lot of people use Google. This is actually how I use Google. I'll start with a high level topic and then I'll learn what questions I need to ask in order to continue getting deeper and deeper into that topic and eventually get to the final answer that I need. So I think this is a great way to use ChatGPT, including for topics in PCB design. Let's try something a little more technical. Let's just start with something like, how do I design a high-speed PCB? So you can see here, even with the default model, it's giving you a lot of pretty high level points to think about. If you look online, including on the Altium blog, you're going to see some pretty generalized guidelines like this. This doesn't really tell you how to design a high-speed PCB. What it actually tells you is what are all the different areas of expertise that are involved in understanding high-speed PCB design. So I think this is again an example where we gave it a high-level overgeneralized question and it gave us a high-level overgeneralized result. I think an interesting result here is point number 1. Under component selection, select components that meet the high-speed design requirements. That is a statement that is so overly generalized as to be inactionable. It's completely unusable. Things like high-speed transceivers, high-speed clock sources, high-speed memory modules, all of that is very overly generalized, and I don't think it really helps you with anything regarding component selection. And in fact, this would be a subtopic in something like signal integrity, power integrity, and EMC. Use simulation tools to validate high-speed design. That's an appropriate statement, and of course, it is a true statement. You probably should do that. Same thing with testing. You should probably test your high-speed design to make sure that it does meet your requirements and does meet your metrics for SI, PI, and EMI. So these are all true statements. Unfortunately, not really actionable in my opinion. I'd give it a B only because it generated overly generalized guidelines for an overly generalized question. Let's do something a little fun here. Let's say we replace high speed with an RF PCB. It's interesting because we get almost the exact same set of guidelines here. And you saw it right here on screen. It generated all of this live. What we see here is something funny. The only thing that's really different here is that we added in RF routing. The RF routing portion, this is actually going to be almost identical as something that would come up under high-speed routing. So there's really nothing specific here. The only thing that actually is really specific here is use a 50 ohm trace for RF signals. And it's not a 50 ohm trace width, it is a width of your traces that gives you 50 ohms for your particular stack up. So I think it's very interesting that it generated this particular sentence because it's kind of nonsensical if you ask me. In any case, if you look through some of these other points, I mean, they are just essentially rewrites of the points that we had here for high-speed PCB. Let's try another example. Let's say instead of high speed, we have high density PCB. So this would be like an HDI PCB. And let's give it a shot. Once again, we get a decent amount of the previous points reproduced. In fact, this point right here, point 6, here we see use simulation tools to validate the high density design. Well, if we just scroll up here to point 6, we see that under simulation for high-speed design, we see use simulation tools to validate the high-speed design. It's almost identical. Essentially, all that was done here was to replace high-speed with RF, and then add another sentence here that's saying it's important. And then here, number 6, to replace it with high density. And here under high density, it just left out the point about frequency domain. However, in a high-speed design, it's also important to perform simulations in the frequency domain to verify performance, because if you were doing simulations with a high-speed PCB, you would be looking at S parameters most likely, and those are in the frequency domain. And so it left that part out for the high-speed PCB. So these types of questions and then the results that you get are very interesting because they're essentially carbon copies of each other with a little bit of variation. All that was done was to take out the one type of PCB and put in a different type of PCB and then reproduce the response. So these results are much more interesting. The reason I think they're much more interesting is because it did a couple of things here as it was generating the response. So the first thing that it did is it did reuse some of the prior points in the GPT 3.5 response. However, first thing that it did is it seemed to know that high-speed or high-frequency designs can be HDI, and indeed I've done some of those designs, so yes, HDI design techniques are sometimes used with high-frequency designs or high-speed designs. Another thing that's interesting is it went a little bit deeper on the manufacturing files, so that's something that you would do at the end of the design. It also seemed to put these in the correct order, which I thought was interesting. So you would generally go through this kind of order where you then plan the stack up first. The thing is, it didn't mention anything about schematic capture, so of course that would come before the actual PCB, but that's okay. Define your objectives. I think this is a bit more overgeneralized as we saw before. However, it is correct. You do need to define your objectives. I think anyone that works in engineering would know that. And then here, as we look through this a bit deeper, it does bring up DFM and DFT. So those are important points, both for high-speed designs, high-density designs, pretty much any other design that you might need to do. It's not that these are incorrect statements. I think there's a bit more detail here, which is nice. And the other thing that it did here is it brought up signal integrity. However, in HDI, signal integrity takes a different approach than it does in something like a high-speed design or an RF design. And the reason for that has to do with the thinness of the layers as well as the width of the traces. So let's do the same experiment we did before with high density, and then let's replace it with high speed. And let's see if it gives us something that just kind of reproduces these results with the newest GPT-4 model. So now this result just generated for a high-speed PCB, and unfortunately it did almost the exact same thing that it did with the GPT 3.5 model, which was to basically just recycle the previous recommendations for a high-density design into a high-speed design. Not all high-density designs are high-speed. They do tend to be, but they aren't always that way. So you would expect to see a little bit of overlap, but this is really interesting because it essentially just copied all of these rules over to a high-speed PCB, and then it replaced high-density with high-speed. Let's try this one more time with high voltage and see what happens. So this result is also very interesting. Instead of just replacing high density with high speed, like we saw in the previous response, now it does actually bring in some of the points around high voltage, namely creepage and clearance, as well as electrical breakdown and arcing. So it did bring in these points correctly. However, it now also took the prior structure and then reused maybe about 75 or 80% of it, and then added in a few things about high voltage. It also kept some of the prior points about high speed and high density, and then applied them here for high voltage without the correct context. So one of the points that it brought in here was power integrity. Now, power integrity does matter in both DC and in AC, so I'm not saying that power integrity doesn't matter for a high voltage design. However, I think you have to distinguish between AC power integrity up to high frequencies, which is important for high speed and typically for high density designs, versus DC power integrity, which is what might be required in a high voltage design. So on that note, we can, I think, go into something a bit deeper and a more technical topic in a new chat. And let's see how well it understands the difference between AC power integrity and DC power integrity. What can I do to ensure DC power integrity in a high voltage PCB? So this is a bit more specific, and let's see what it comes up with. So these results are pretty interesting too. So first thing I notice in this list of recommendations is number one, DFM. Not really germane to DC power integrity in a high voltage PCB. When we worry about DC power integrity, we're generally worried about reducing or minimizing IR drop, so reducing any DC voltage loss along the span of those conductors. So to do that, you would care about using things like fat rail or power planes. There could be a bit of DFM going along with that to ensure that, for example, you don't put things too close together, but that has a lot less to do with ensuring DC power integrity than it does to just making sure the board is manufacturable. So we have a little bit of overgeneralization here. This is pretty general. Here there are some other instances where we have like power planes. Now, power planes, using a dedicated power plane for high voltage supplies, that's actually not the only way to design a high voltage PCB with DC power integrity. You don't necessarily have to use a dedicated power plane. You could actually have a single layer that has multiple fat rails on it, and that would probably be enough to ensure DC power integrity depending on your voltage and current values at which you're operating. One thing it didn't mention here was the use of heavy copper, and so this would fit in with stack-up design and material selection. And actually, it doesn't really say anything about stack-up design or heavy copper. And then here, plan for thermal management. High voltage components may generate more heat. Not necessarily. High voltage components that also dissipate a lot of power might also generate more heat. You could also have lower voltage components that operate at high current that generate a lot of heat. So I think you have to be careful with some of this or understand the context around it in order to take some of these guidelines seriously. Connect all grounds to a common point to minimize ground loops and reduce noise coupling. I mean, the point about ground loops is technically correct. The noise coupling instance could be correct depending on the situation you're looking at. If we're talking about DC everywhere and there's only DC offsets between all these different grounds in your system, then there wouldn't actually be any noise coupling at all. But in general, yes, you do want to have a single common ground if you can to ensure proper grounding. And we've talked about this in other videos. There are some other points here with, using ground planes that are pretty general. That's fine. Here with power supply decoupling, I thought this was kind of interesting because typically in a high voltage PCB, you may not actually have a lot of these integrated circuits that need a bunch of decoupling capacitors. Again, a little overgeneralized. Some of these statements are very correct. Some of these statements require some context to understand their correctness. This one is very overgeneralized as well. High quality capacitors, inductors, and other passive components. What exactly is a high quality capacitor, inductor, or other passive component? Well, this is something where I would drill down a bit more and just ask it, what exactly is a high quality capacitor, inductor, or other passive component with suitable voltage ratings and low parasitic elements? That was mentioned in the previous response. And let's see what it says. So here's our result, and we can see here that it basically only generated some guidelines for capacitors. It didn't generate anything for inductors or passives. And it just essentially says that exhibit superior performance, again, a little overgeneralized, reliability and stability in the given application, particularly in high voltage environments. So I think this is another instance where you would have to really keep drilling down, asking it, what is superior performance? What does it mean to be reliable? What does stability mean exactly? And eventually you could probably pull out some deeper results that are related to all of these different areas. It only broke down to capacitors and it basically paused here and then it just stopped. So what's the grade on this set of responses here? Well, I would probably give it a B again. It does bring up things that are correct at a high level. When you start to drill down, it actually failed and it couldn't go beyond capacitors. So that's a bit unfortunate, such is the system that we have available. Just because we go through and we do this exercise, that doesn't mean it can go through and actually do the hard work of building a PCB for you. That is where you have to go back to this portion right here in our previous response and look at the very first point that it brought up, which is define your objectives. You're the one that's going to be in charge of making sure this board gets built to spec, and that means you have to understand the requirements and constraints of your project. And this is something that an AI just can't do. You as the human are responsible for this, and then it is your job to implement the process that actually gets this thing built. So an AI might be able to give you little bits of knowledge along the way. Some of it comes at a very high level and might not be specific to what you need. Some of it can actually drill down a bit deeper and give you something very specific, and it can help you move a project along. My verdict: I like ChatGPT. As you can see here, I've used it to get very targeted information on things that I need to do in my own designs and for work with clients. However, I don't rely on it for these all-encompassing guidelines that would be needed to figure out how to design a new piece of technology. There are actually a lot better outlets for you to find that knowledge. There are webinars out there. Obviously, what we do on the Altium blog tries to provide that knowledge. And of course, YouTube is a treasure trove of knowledge on all sorts of different topics in electronics design. Add this tool into your tool belt, and you'll be able to drill down to specific topics as you need it and become a better designer. So we've just seen a bunch of instances where ChatGPT can give kind of a mix of overgeneralized and somewhat specific results. So now I want to show something that can happen with PCB design topics that is a much more specific question, and so it demands a very specific answer. And I tend to run into this somewhat often. Let's take a look here. This set of prompts that I have here all started with the question, what is the differential impedance requirement for traces in the PCIe 6.0 standard? Now you can see here that it does list a impedance requirement of 85 ohms for these traces. And then it says it's the same in the 5 and the 4 standards. I asked it, what is the differential impedance requirement for the PCIe 3.0 standard? It says PCIe 3.0 is 100 ohms, same as in the 2.0 standard. And then it says here that they all have different requirements, and that is correct. The next question here, what is it in the 1.0 standard? So you can see here in the 1.0 standard, it says a differential impedance requirement of 85 ohms, which is the same as in the 2.0, 3.0, 4, and 5 standards. So this is where you start to get contradictions when you ask it very specific questions. So this is very important because eventually what you have to do is you have to start challenging it when it gives answers that are contradictory. So you notice here, it says that this value was the same for 2, 3, 4, and 5, but the previous answer said that 3 and 2 were different from 4 and 5, which is correct. Now you have to start challenging it. Which one of these two is correct? And then it will often say, I apologize for any confusion, yada yada. You can see eventually it gets down to a specific answer that it will settle on. And it says here, the differential impedance requirement in the PCIe standard was changed from 85 to 100 ohms with PCIe 2.0. I asked another question. Texas Instruments says this, but you're saying it's 100 ohms. Why is there a difference? So sometimes you have to keep going deeper and deeper and deeper in order to get it to resolve these contradictions. And I find this comes up quite a bit when I'm asking these very specific questions about a very specific interface or standard or practice or circuit, something like this. Sometimes it will give these very contradictory results and you have to keep pushing it. And eventually it's just going to go back and forth between these two different answers and try and give you something that appears correct, and you may not ever land on the correct answer from this system. So we've looked at a lot of knowledge generation queries so far. What about some design-focused queries that are a bit more about some of the tasks that you might have to actually do in a design on a daily basis? Well, let's have some fun here. One of my favorites is select a component type of query. Let's suppose that I need a transimpedance amplifier that can support a 4 gigahertz signal. Provide a component that can meet this requirement. And let's see what happens. Now, this is one of the components that might support this, and indeed, if I just go over here to Google, and then I just look up this particular component, I can then check and see if this is really going to meet that requirement. Now, this part is unfortunately obsolete. So you can see here, it already provided an obsolete part. So why don't we continue with this? Provide another part that has higher gain bandwidth product and is not obsolete. Now let's check this one. Unfortunately, I think this is also a power amplifier and is not appropriate for this type of application. So just taking a look here, we see that this is a 0.5 watt distributed amplifier operating from 0.1 to 30 gigahertz. So it's actually not a transimpedance amplifier. Very interesting here, although it is a power amplifier. So you could do something with this, but not exactly for the type of application we're looking at here. So let's try one more time because there's a particular component that I want it to push. So what I'm going to do now is ask it, is the OPA 855 appropriate for this application? So finally, it gets to a particular component that actually would be suitable up to this 4 gigahertz signal, but only with pretty low voltage to voltage gain. And that component is the OPA 855 from Texas Instruments. So this is kind of unfortunate because I had to actually prod ChatGPT to give me the correct answer for this type of component. Let's try again. Provide 3 power regulators that can support wide input voltage from 9 to 40 V DC and output 12 volts DC at, let's say, 25 watts. And let's see what happens. So here are 3 possibilities, and these are all LM26X components. This is a Texas Instruments integrated circuit. It is a DC-DC regulator, and this is one of those things where you would want to just check to see that it can actually provide the power output that you want. Now here we see 12 volts DC, but we also see from this particular information provided by Texas Instruments that this is a 1 amp output. So this won't give the power output, but it would give the wide input. The other issue here is that this particular product is out of date, although not necessarily obsolete or end of life, but you can see here that Texas Instruments recommends a newer product that's available. So this reflects one of the issues with ChatGPT is, of course, that its data set only goes up to a certain date and then cuts off. Now let's look at one last query, this time from RF design. So let's suppose I have a grounded coplanar waveguide. I want to calculate the impedance of this grounded coplanar waveguide. Let's see what it says. So here it does spit out an answer. Now let's just, for fun, do a new chat, but with GPT-4 and see what it says. So the result here is very interesting. So first, with GPT 3.5, it does calculate an impedance, and we see here that it gives us 64.7 ohms. Now, interestingly, it actually uses the effective dielectric constant value or result for microstrip lines, which is not necessarily valid for all other lines. Then it goes through this calculation using the width of the transmission line and the thickness of the substrate to get us a value for an impedance. Next, when we do GPT-4 and we try to go through the same process, same question, same geometry, we see that it actually doesn't return anything because for some reason GPT thinks that it needs the length of the line in order to calculate the impedance. And as anyone who knows about distributed element circuits knows, that you don't need the length of the line to calculate the impedance, including for a transmission line. These are interesting results, of course. Be careful with this because unfortunately I think both of these results are incorrect. And what I'll do is I'll go into another video that goes deeper into grounded coplanar waveguide impedance calculations in another video. For now, I'm going to stick with a field solver to calculate the impedance of a grounded coplanar waveguide, something like Symbior or ANSYS HFSS. Thanks for watching this video, everybody. Hopefully this gives you some context around what ChatGPT can and cannot do. Of course, it can give you some high-level knowledge that you need to help raise your level of skill and expertise as a PCB designer. And I think the best thing that it can do is it can tell you what you don't know, and you can figure out what questions you need to ask next. Unfortunately, when I start to get down to some very specific technical topics, it can contradict itself, and I see that quite often. I just showed an example with PCIe standards. You can find other examples of contradictions if you start playing around with ChatGPT on your own with very specific technical questions. Also, watch out for overgeneralizations. We saw several examples involving high-speed design, high-density PCBs, and RF design. A lot of those recommendations just get recycled over and over again, and I don't think it's very actionable. However, like I said, it does give you some context as far as where to look next, and what questions to start asking next. Thanks again, everybody. Make sure to hit that like button, hit that subscribe button. You'll be able to keep up with all of our tutorials as they come out. And of course, it will help you stay at the cutting edge as tools like ChatGPT start to make their way into engineering and electronics design. And last but not least, don't forget to call your fabricator, everybody. We'll see you next time.